All right, thank you very much for the organizers. It's really a great honor for me to be here. Okay, so I've given you a general enough title, and so we'll see where this leads. So first, a bit of history. So I unfortunately do not have any pictures of me and Nick together. Maybe someone can take one before the day is over, so I have some proof that we have coexisted in the same space. Okay, so my history with Nick goes only back to April of 2016. I was a postdoc at New York University, and Nick was visiting, and he gave a talk at our numerical analysis and scientific computing seminar on multivalued matrix functions. And so, as is tradition, we take the speaker out to lunch afterwards. And so I was lucky enough to be sitting close to Nick, and he mentioned to me at some point, I have some problem with GMRes. I wonder if we can talk about it. And so Nick stopped by my office after lunch, and he told me this idea of iterative refinement, and maybe we can use these LU factors as preconditioners in GMRes instead of just doing the triangular solve within the inner loop. And so I said, okay. And so, then Nick went back to Manchester, and like Dennis said, you don't want to disappoint Nick Hyam. So I set to work on this, and a little while later emailed some results to Nick. And again, he was very courteous because I'm sure these initial results I sent him was just terrible. But we iterated on this and refined it. And over the course of that year, we wrote this first paper together on GMRes based iterative refinement. Okay, so then around that time, so in 2017 was right when NVIDIA had come out with this V100 GPU that had these half precision tensor cores. And so I don't remember the exact timing, but Nick was at had a meeting with Siam in Philadelphia and made a stopover in New York, and we had a brief meeting together, and he mentioned to me, I think we can do this in 3 precisions, why not? And I remember him saying to me, I think that this could have really big impact. And so for me, this is my most highly cited paper that came out of that brief discussion with Nick. So thank you very much, Nick, for that. He invited me that summer to visit Manchester. And so we finished the work on the 3 precision iterative refinement paper. I also visited here the subsequent summer, and we worked on applying this to least squares problems. And that paper took a little longer, but that was my own delay. Okay. So my talk again will be based on mixed precision. And so we all know and love double and single. When I started working with Nick, this FP16 and BFloat16 formats had just started to come out. And now, just earlier this year, now the NVIDIA has a GPU with even quarter precision. And there's 2 different variants, depending on, you can put 1 more bit in the mantissa or not. Okay, and so here is just a table. So giving here's the double precision, single precision, the 16-bit formats, and the 8-bit formats. And you can see here the advantage. So this is the kind of the best performance you could hope for on the latest NVIDIA H100 GPUs. And so you can see there's a clear benefit, right? We can get much better performance if we can make use of these low precision formats. Okay, the trade-off is, right, we have less precision, right? So this U will be the unit round off throughout my talk, and we have a smaller range of representable numbers. So which of these formats is most appropriate for you to use will depend entirely on the data you have and how much precision accuracy you need. Okay, so if we take a nice small number like 60, for example, okay, that falls nicely into the range of all these formats here. Although if you use this E5M2 format, the 60 unfortunately gets rounded up to 64. Okay, but if you use stochastic rounding, you might get lucky and it's only 56. So if you try and use fewer bits than that, it might overflow to infinity, so we're not going to go there. Okay, and so there's a long history of using mixed precision in numerical linear algebra. In iterative refinement, this goes back to Wilkinson in the 60s, and Gerard Morant recently pointed out to me that Doolittle was even doing this much earlier than that. Okay, and so there's been a lot of work in developing BLAs that exploit these tensor cores, iterative refinement, like I said, for both linear systems and least squares problems, matrix factorizations, eigenvalue problems, both dense and sparse direct solvers, orthogonalization, multigrid, and iterative methods. And so there's a couple surveys that you can look at, one of which was written by Nick and Theo in just this year in Acta Numerica. Okay, so there's my papers with Nick, which I'll highlight. Okay, so when can I get away with using low precision? Okay, so in the scientific computing or data science world, we don't just worry about floating point arithmetic. In fact, people often just kind of ignore that because we're dealing with so many other errors that are usually of much greater magnitude. Okay, so just to start off with, we're working with imperfect data. Okay, we have a precision with which we can measure the data that's going into our matrix on right-hand sides. We have modeling error, discretization error, and a lot of the times we're usually making some intentional approximation at the algorithm level in order to get better performance or to reduce the memory and things like that. Okay, so there's just some examples of that. Our model order reduction, using low rank or hierarchical approximations, or doing some kind of sparsification, or using randomization. Okay, and so you might ask, okay, so given that you're already working with so much inexactness, do I really need to be using double precision for all my computations? And the answer, I think, is usually no, in a lot of cases. Okay, and so I will steal this analogy that I've heard from Rasmus Tamstorff, where if I think of these nails as my errors, right, there's no point in hammering down the finite precision error so small when I have all these other nails still sticking up. Okay, so I like this analogy. It captures it very simply. I will point out that it can be more complicated than that. Okay, and so here's one example that I know of that's dear to me, where things can be a little more complicated. All right, so if we look at just running the conjugate gradient algorithm in finite precision, okay, so I have a very simple matrix here. So my matrix is just a diagonal matrix, condition number 1000, with equally spaced eigenvalues. Okay, my right-hand side is just a vector of ones, very simple. Okay, so here I'm plotting the iteration on the x-axis and the relative error in the A norm on the y-axis, with double precision in black, blue in single, and red in half. Okay, and so if you look at this, you say, oh, okay, my other nails are much higher here. I can get away with using half precision here. I only need 10 to the minus 4, 10 to the minus 3. That's fine. I could run CG in half precision and lose nothing. Okay. But this is not always the case. Okay, so here is a matrix, same condition number, same largest and smallest eigenvalues, but the distribution of eigenvalues is different. Okay, so here I won't say they're clustered, but they're accumulated towards the left side of the spectrum, so that I have large outlying eigenvalues. And this is actually a known case where CG is more subject to the effects of finite precision error when there are large outlying eigenvalues. Okay, so in this case, I'm not just losing accuracy. The accuracy might be fine, but I'm also converging much slower when I use lower precision. Okay, and so that can kind of detract from some of the performance benefits that I might see if I have to do many, many more iterations. Okay, so we should hammer our nails down, but we have to be careful doing so. Okay, so I'll talk about some recent work of mine today. And so this is joint work with my postdoc, Eva Daugitskete. And so in our setting, all right, so we want to solve systems of this form. So I have a square matrix A, it's symmetric, positive, semi-definite. Okay, I have some shift parameter here, and so this will make A plus mu I positive definite. Okay, and I'm going to assume in our desired case, A is going to have rapidly decreasing eigenvalues or some cluster of large eigenvalues. And so this comes up in many applications. So regularized least squares, for example, in ridge regression. Okay, and so I want to solve this system using the precondition conjugate gradient method, and I'm going to use preconditioner, and I'm going to use a spectral limited memory preconditioner. And so there's a lot of work on this. So my matrix, or my okay, so my preconditioner P has this form. I can also write out its inverse. Okay, and so U here, so this is an n by k matrix whose columns contain approximate eigenvectors of A, and they're orthogonal. And so my theta here is diagonal that has approximations to the eigenvalues of A. Okay, so this comes up in data assimilation, which Jennifer and others have done a lot of work in. Okay, and so what do I need to do? I need to, in order to construct my preconditioner, I need these approximate eigenvectors and approximate eigenvalues. Okay, so I'm going to obtain them using a randomized Nyström approximation. So I want to compute some rank K approximation using the Nyström method. Okay, and so my Nyström approximation takes this form here. And so Q is my test matrix. We're going to use a random projection. And in the case that, so you could pick Q to be based on the columns of A somehow, because the quality of this approximation is going to depend on the range of Q. So in the case that A is very large, we're just going to use Q as just a random orthogonal matrix. And so I want to avoid matrix products with A. So I'm kind of assuming that doing A times something is the bottleneck in my code. So we're in the setting where A is very, very big. Okay, and so here is how this works. And so this algorithm is from Trop et others. So this is a stabilized version of this. Okay, so first I'll generate a random Gaussian matrix. You don't have to use a Gaussian. You could do something more structured if you wanted to, but I'm just assuming a Gaussian here. Okay, I will take its QR factorization. Okay, and then here I'm going to do Y is A times Q. So that's my expensive part here. That's the big matrix times some vectors. Okay, I'll compute some shift. To shift to this Y, I'll do Q transpose times Y, and I'll get this tiny matrix B. Okay, I'll do something to make sure Cholesky doesn't fail on me to get this Cholesky factor. Okay, I will solve on the right, and then I'll do the SVD of the result, and I can get out my U, which is what I want, and then the singular values, and I'll kind of undo the shift that I did, and then I can construct the eigenvalues. Okay, so the question is, given that this is the most expensive cost here, right, doing this matrix times these vectors, can I reduce that cost by actually doing that in lower precision? Okay, and so again, here are my two nails here. Okay, so I can write the total approximation error as the sum of these two errors. So this A sub n is going to be the Nyström approximation if I computed everything in exact arithmetic. Okay, and the AN with a hat is going to be what I actually get when I do it in finite precision. Okay, and so usually I'm if I want a pretty low rank approximation, this error here this exact approximation error will be pretty large, and so I can hammer down my finite precision error to match that. Okay, and so there are existing results on the exact approximation error. So a deterministic gap bound was given by Gittins and Mahoney. And that could be pessimistic. There's also an expected value bound that's given. Okay, all right. So our goal. So someone's already done the exact error. We want to look at the finite precision error. Okay. So again, my finite precision error is the difference between the exact Nyström approximation and the one computed in finite precision. Okay, I'm going to make the simplifying assumption to start off with that this is the only part I'm doing, let's say, inexactly, is the matrix product A times Q. All right, and I'm going to do that in some precision called UP. All right, everything else is done in a working precision, which I'm going to assume is much smaller. We could do away with that, and but it would just complicate the analysis. Okay, and so you do a couple pages of analysis. I won't bore you with that, but we can write down a bound of this form. Okay, so the difference between the exact Nyström approximation and the finite precision one, okay, is bounded as some factor of the precision with which I'm storing the matrix and computing this matrix product, some dimensional constant, which is much larger than you actually see in practice, very worst case, and then some norm of A. Okay, and so so I'm gonna fudge the dimensional constant because we really don't see end of the 5/2 in practice. So what is my interpretation? So what does that mean? So I want to know, when is my finite precision error going to be larger, grow larger than the exact approximation error? And I can say that will happen when this ratio, this k plus first eigenvalue divided by the largest eigenvalue is around square root of n times UP. All right, so this kind of gives me, if I know something about the gaps in my eigenvalues, I can kind of figure out, okay, what precision can I use here and get away with? All right, and intuitively, the more approximate, the lower rank representation we want, the lower the precision we can use. Okay, so now, like I said, we want to use this as a preconditioner in the conjugate gradient method. Okay, so how good of a preconditioner is it going to be? All right, so I'm going to define two quantities here. So this E is, so just to simplify this so I don't have, so it fits on one slide, I'm going to call the exact approximation error E, and the finite precision error is curly E. Okay, all right, so here's my limited memory preconditioner. So how good is it? All right, so I will again stress that, as I just showed in the previous slides, condition number does not tell you the whole story about CG, but you can say if the condition number is small, then you will converge quickly. Okay. All right, so then we have these bounds. Okay, so this first expression gives me a lower and an upper bound. Of course, this only holds if this mu is greater than my finite precision error. Otherwise, this falls apart. And in the case that A is positive definite, then I have another upper bound, which also holds. Okay, so these red quantities here are the ones that show up now because we've taken finite precision error into account. Okay, and if you set that to 0, then it reduces to the bounds that have already been proved for the exact case in the literature. All right, so let me just show you a numerical example of how this works. So this is a matrix from the sweet sparse collection. These are just small problems. You can find our code for running this here. Okay, and so here this is just to give us some intuition. What can I expect to work? Okay, so here's the value of K, right? That's the rank, let's say the rank of the Nyström approximation I'm taking. Okay, here I'm plotting, these are just kind of scaled, those are normalized singular values. So K plus 1 over the largest one. All right, and here's square root of n UP for half, and here's square root of n UP for single. Okay, and so what we can intuit is that, where this crosses, that's about when I'll start to see the finite precision error dominate. Okay, and so if we look at that, that's the case. All right, so here blue is exact. Okay, purple is using half. Yellow is using single, and orange is using double. And so, you do see around, 200 to 220, that's where the half precision starts to give me a deviate, let's say, and you can see the effects of using the lower precision. Okay, but for single, fine, you could use that no problem at all. Okay, and now we have also the mean finite precision error. Again, so these are the actual measured quantities, and these are the bounds. So you can see the bounds are, given a pretty big overestimate in most cases. Okay, and so what about its use as a preconditioner? Okay, so here I have, I'm plotting the condition number. All right, so the markers show the actual measured quantity, and kind of the lines are giving the upper and lower bounds. Okay, and so here we have, we can see that again around 200 to 220, around 218. That's where we see a deviation of using half precision, which is predicted by our heuristic. The bounds, however, for half precision, especially the lower bound, is kind of useless in this case. Okay, and what about the number of iterations that we actually see in the preconditioned conjugate gradient method? Again, until we need a rank around 218, 220, we really don't see much effect at all of using half precision. So we can totally get away with it. Okay, and so just to say we did try some things in quarter precision. I'll say for the problems we tried, it didn't really work very well. Okay, it doesn't really give you very much. So here, this is the same matrix I was using before, this BCSSTM07. Actually here, when we use quarter precision, and this is the variant with 3 significant bits, the iteration count goes up. Okay, so it's a terrible preconditioner. We did find one example where the iteration count does go down, so it's the preconditioner is doing something, but if you look at the y-axis here, it's not doing very much. Okay, so is there a use for quarter precision? I believe that there is. Maybe we have to do something more clever here to get it to work for us. I don't know. Okay. All right, and so just to self-advertise a little bit while I have your attention. So I've Nick was really inspiring for me, and I've done a lot of work on mixed precision numerical linear algebra since then. So this is a lot of work for me, and also for my PhD students. So we've worked on multi-stage mixed precision iterative refinement, using recycling in these methods, using different types of preconditioners, and also using mixed precision in S-step conjugate gradient methods. Okay, so to summarize, we are living in a multi-precision world. I am a multi-precision girl. This is kind of it's an integral part of supercomputers now. Like Jack said yesterday, if you're not using the GPUs, go home. So if you're not using mixed precision capabilities on GPUs, you can probably also go home. There's a huge amount of opportunities for using mixed precision. Like I said, we already have all these approximations that we're doing in our simulations and what we do every day, and there's really we probably don't need to be using double precision for everything. Okay, so it's time to go back and take a look at that. But we also face big challenges in actually, getting things to work, getting speed ups, and actually proving that things will still be okay. All right, so happy 60th birthday, Nick.